Hello, welcome to the Sudokult discussion, which is used to be called the Sudokult podcast, but it's not really a podcast. It's a YouTube series, so we renamed it. But it is exactly the same content that you'd expect from the last two episodes. And I am David Clamage, also known as Rangsk, and I also have with me
Philip Newman.
Yeah, and Philip is going to be leading us again, and today we are going to be discussing Set, which stands for
Set Equivalence Theory.
Yeah, and
then kind of a recursive acronym sort of thing. Because I think those are funny.
Those recursive acronyms are definitely amusing. So, and it's kind of an allusion to set theory in mathematics, but actually is not. Not at all. So don't get confused there. But it's just a fun play on names there.
Yeah, there's even a puzzle that we're going to talk about today called Set Theory, which doesn't make any sense with the acronym, but that's
well, yeah, that's the problem with these acronyms is like pin number and ATM machine, right?
Right.
It doesn't make sense just to say set, even though the T stands for theory. So you end up saying set theory, which is theory. So
yeah,
and that set stands for set. So anyway, with all that said, first I think we wanted to start by going over the puzzles that we had last episode and going over how to solve those based on what we discussed in those episodes. So, Philip, do you want to take away on that?
So, we had 3 puzzles last week. The first one was called The Final Countdown. And it's a little bit of a hint on how you solve it. So, at the start of this puzzle, these 3 5s see into box 5, and we can actually place a hidden single 5 in the cell. After that, we're going to look at 4s. That's kind of what the title is hinting at. We're going to be counting down. And we're going to look at rows 2, 4, and 8. The reason we're going to look at those rows is there are a lot of givens in those rows that are not 4. And additionally, this 4 in box 3 rules out all the cells in box 3, including this one. So in these rows, we can't have 4 in any of the highlighted cells. We also can't have 4 in the 2 columns that already have a 4. So in the rows, that only leaves 3 places for 4, and they're in the same 3 columns. So we have a swordfish, and we can eliminate 4 from all of the remaining cells in those columns.
Those are what we called the cover. Were they called cover sets or cover?
Right. So the row 2, 4, and 8 are called the base sets. That's where we need 3 4s. The cover sets are where we can get 3 4s. And the most 4s that we can get in those columns is 3. So they have to appear in the green cells. Otherwise, we're going to run out of 4s to place in the base sets.
Right.
So the result in this case is in row 6, we've removed these 3 cells. It already couldn't be these because of the givens and because of the 4s. So we get a 4 right there.
Very nice.
Similarly, there's a swordfish on 3s. That's going to put a 3 right there. And then there's 2 jellyfish on 2s and 1s. And I'm not going to show those. You can look at them separately if you want. But the end result is that you have fish on 4, 3, 2, 1. And then you end up with a bunch of hidden quads that you can use to finally finish off the puzzle. So
all right.
That's how that one works. And we will be revisiting this at some point using set. So
nice.
All right. This is ripples. And this one has finned fish. So I'm going to show the one on 1, let's say. And just like in the previous puzzle, there are a lot of givens that are lined up. And this is a common theme in a lot of my puzzles, especially, that have a lot of fish in them. I'm just going to gray those. We know that the digit 1 can't appear in any of those cells because there's already a given there. Do you want to look at columns? I think columns are probably the better choice here.
Sure.
Yeah, so let's look at columns 1, 6, and 7. Where does 1 go in those columns?
Looks like it's only 3 places.
So it's these places. Because our given ones are in rows 2 and 5, they eliminate those cells. But also the cell right here. Those are the places that can hold 1 in those columns. And we don't quite have a regular swordfish because we have this extra cell. There are 4 rows that can take a 1 in that column.
Right.
So what we do here, these are our cover sets, the rows. Because this time our base sets are the columns. So if we had a regular swordfish, if this was not true, then we would eliminate 1 from all of these cells. Right?
Yep.
If this is a 1, then we eliminate from all of these cells. Right?
Yep. Mm-hmm.
So the overlap, these 2 cells, is where we can eliminate 1 with the finned swordfish.
And actually, there's already a 1 in one of those columns, so it's just one
there's
cell.
already 1 here.
Yeah.
So it's just 1 cell on 1. But this fin is also useful for all of the other digits, 2, 3, 4. Only those are jellyfish instead of swordfish. So what you end up doing is ruling out 1, 2, 3, 4 from all 4 of those cells.
I see.
Yeah. And then you can play some singles and solve the puzzle. So
very nice.
That's how that one works. There's some similarity here to the Chironex puzzle that David did on his channel. So, all right, the last one is a Franken swordfish. So this one uses boxes. And this time it's on 8 and 9. I decided to mix it up and do it on the high digits. So obviously 8 and 9 are restricted in this row.
Right.
So they're also, let's pick 8 to start with. It doesn't really matter. Also somewhat restricted in these rows. You can see we have a lot of givens lining up in columns 1, 2, 8, and 9.
Right.
But we can't cover all of those with just columns. There are 5 columns that can hold 8. Well, this column can't hold 8, but there are 4 columns that can hold 8.
Yeah.
I highlighted more green than I intended to. That's okay. So how do we do it? We need to use something other than columns.
Right. So we can cover with column 3 and 7 and also use box 5, looks like.
Right. So these are our cover sets. So we still have 3 rows for our base sets, and this time we have 2 columns and a box for our cover sets. But the same principles apply as for regular swordfish. We can eliminate 8 from any cover cell that is not a base cell. So in this case, that's going to be all of these cells in column 3, all of these cells in column 7, and these 2 cells already couldn't be an 8, but I'm going to go ahead and highlight them anyway. Actually, not that one. I'm going to put these back in green. Put those in red. I'm going to go ahead and highlight them anyway because this also applies to 9. Exactly the same thing. So 8 and 9 are ruled out of those cells, and you can proceed from there. This one is solvable using other techniques. I think you can use maybe a couple of kites or empty rectangles, and then a slightly more complicated turbot fish. But
and that's going to be the case of a lot of puzzles. Where
a lot of puzzles are like that. You can do multiple different ways. But this is the quick way to do it if you see it. So
yeah, and if you ever like see people gushing over how good, say, Shai's puzzles are, her classics, it's because she not only really shows sort of a quintessential way that the technique works, but she also makes it extremely difficult to bypass.
Right.
So that's definitely a skill and huge time investment to construct the puzzles.
Yeah. Honestly, when we're setting classics like these that are targeting one trick, we probably spend more time making it not bypassable than we do making it unique. Because it's so easy to add a given and just the thing completely collapses into singles. So,
and I know a lot of people have questions on how to set those things, and I think what they aren't, maybe they do understand it, but I don't know if they're understanding the scope of how much time and trial and error is involved in the setting. Yeah. And so there's, it's pretty easy to initially set up a puzzle that's probably not broken, that does demonstrate a specific technique, but then making it unique without breaking it and making it not super easy to bypass that technique is the majority of the time spent. Sometimes you just have to scrap it and try a different way to do it. So,
and you do get better at it with experience, but even after you've done a lot of puzzles, you will still run into something that takes you hours and hours of trial and error. Right. That's the way it works. So, all right. So we're going to talk about, I'm just going to get rid of our highlighting here. We're going to talk about set today. So I'm going to come back to this puzzle in a little bit. I wanted to start by looking at this puzzle. This is called Set Theory, which stands for Set Equivalence Theory, Theory. So this is actually a computer-generated puzzle. This came up. I do searches for very, very hard puzzles. And the way that the hard puzzles are rated, it's more based on chains. So the more complicated a chain that you need, the higher the rating it is. So if you know what Sudoku Explainer is, this is an 11.6. Maybe at some point we'll talk about different tools and rating systems.
That would be
so if you don't know what that is, that's totally fine. The hardest known are 11.9, so this is not far off that. But this is actually a very approachable puzzle if you know set.
Which means it's both an impressive technique and also one that computer solvers, at least at this time, are not using. Yeah,
there's one solver that we use frequently that supports MSLS, which we're going to talk about, is very closely related to set. And there are some other solvers out there that do some advanced techniques along these lines, but it's not that common. And it's definitely not common to be used in rating puzzles. So
yeah.
All right. So what I want to start by doing is looking at this with the MSLS approach. This is how...
If I can interrupt.
Yeah, go ahead.
We did have a comment on our last episode that we use a lot of acronyms.
Sorry.
And no, I mean, we're used to them, right? But yeah. I think if we just use the full name and then the acronym at least a few times before we switch purely to the acronym, I think that'll help people follow along. So MSLS is, I'm trying to remember. So is it mean sector locked sets? Multi-sector locked sets. See, even I don't quite know what that means. But
yeah, and I was intending to say it again and totally forgot and just use the acronym because that's...
Yeah. So please feel free to ask in the comments if we use some acronym you don't understand. We'll do our best to, avoid just randomly using it without explaining it. And so multi-sector lock sets is what MSLS stands for. And I think the name multi-sector lock sets is confusing enough that it may not even be any better than just calling it MSLS, but at least now you know what it stands for.
So I am going to explain what it is. So hopefully it will make a little more sense why it's called that. The first episode that we did a lot on alternating inference chains, but we also talked about almost locked sets. So an almost locked set is where you have, say, 3 cells that can hold 4 different candidates. If it could only hold 3 different candidates, you'd have a naked triple. But if it can hold 4, that's called an almost locked set.
Yeah, and so a naked triple would be a locked set.
Right.
So almost locked set is exactly what it sounds like.
Right. So a multi-sector locked set is, like the name might suggest, a locked set that involves multiple sectors or houses. We tend to call them houses. So rows, columns, or boxes. So
it could also be named a multi-house locked set. That would be kind of an equivalent name.
Yeah, which would be just as confusing.
Yep.
And probably the acronym would be more awkward to say.
Yeah, that's true.
MSLS just kind of flows off the tongue. Not really, but anyway. So this was developed, I'm going to get the year wrong probably, around 2012, as an approach to generalize fish, generalize not just fish, but generalize lock sets in general, generalize almost lock sets and how they interact with each other. So one of the things we talked about on episode 1 was a almost lock set ring, which is where 2 almost lock sets see each other and basically make each of them a lock set. You just don't know what order. So that is an example of a multi-sector lock set. I'll actually just go ahead and show that here. I have it up. This is the awkward lazy snowflake puzzle from the first episode. And this is the almost lock set in row 3. We have the candidates 1, 2, 3, 6, 9. And then the almost lock set in row 7, we have 2, 3, 4, 6, 9.
Yep.
And in column 2, the 6s see each other. So only one of those can be 6. And in column 8, the 9s see each other. So only one of those can be 9.
Yeah. And kind of as a reminder from episode 1, the 6 and the 9 only appear once each within the almost lock set, which means one of them must appear.
Right.
We kind of explained
if we didn't have a 9 here and we didn't have a 6 here, we'd have 4 cells that need to have 1, 2, 3. And that's not going to work.
Now, of course, both could appear, but we can't
both could appear.
Both gone.
So if we just look at row 3, both could appear. And if we just look at row 7, both could appear. But because they both need at least 1 6 or at least 1 9, and there's only 2 6s or 9s that can appear in them combined, you end up deducing that one of the rows has a 6 and one of the rows has a 9. And it becomes a locked set of sorts. Since it involves 2 rows, it's a multi-sector locked set. So that's roughly what MSLS is doing. In this case, it's saying I can have 1, 2, 3 in this row. I can have 2, 3, 4 in this row. That's 6 digits. I can have a 6 in this column, and I can have a 9 in this column. So that's 8 total digits. And I have 8 cells.
So probably the part that people are already scratching their head and confused about, because I'm kind of thinking the same thing, is why in this case are 2 and 3 considered 2 different digits from each other, but 6 and 9 are not considered 2 different digits from each other.
How do you mean 2 different digits?
So when you were counting, you said 1, 2, 3. That's 3 digits.
Right.
And then you said 2, 3, 4. Now we have 6 digits, right? So but 2 and 3, last I checked, are the same digit as each other.
Right.
So why are those counted as doubled up? But then when you counted the 6 and 9, you didn't say 10 in 8.
I understand. So we have 8 cells, right? Those 8 cells have to have some digits. So what MSLS is doing is trying to figure out how many digits we can actually put in those cells. So there's a limitation in the rows and in the columns. The reason we consider 6 separately is because it's the only digit that we care about in this column. It's limited in this column. 9 is limited in this column. In the MSLS and the ALS XZ ring. 1, 2, 3 can appear in these cells. We can't put 4 digits from 1, 2, 3. That's the real limitation. If we had an extra digit here, if these could be 1, 2, 3, 4, we wouldn't have a problem and require a 6 or a 9, if that makes sense. So 1, 2, 3 are limited in the sense that we can only use 3 of them in the row. They're not limited in the sense that they have to appear in a particular place, or even if you're just looking at the row, that all 3 of them have to appear. This could be a 6, and this could be a 9, and that seems fine, and then we only have 2 of 1, 2, 3. We know that doesn't work, but if we're just looking at this one row.
Right.
So what we're counting here is from 1, 2, 3, how many of them can we put in this row? We can put 3.
Right.
From 2, 3, 4, how many of them can we put in this row? We can put 3.
Yeah.
From 6, how many of them can we put in this column? We can put 1. From 9, how many can we put in this column? We can put 1. So we have 8 total digits that we can put in those 8 cells, considering the rows and the columns that we looked at. Now, the last important little bit is that covered all of the candidates in those cells. If we had any other candidates, say this could be a 7, it can't, but if we had another candidate here, then the whole thing falls apart. We have an extra candidate. Effectively, we have an almost MSLS.
Yeah, AM.
Right.
I can't even say it. AMSLS.
One of my puzzles is actually named on the basis of adding A's to MSLS. Anyway, okay. We'll get to that later.
Now you may be thinking, while listening to this explanation, boy, I wish there was an easier way of thinking about MSLS.
Exactly. Yeah. That's why we're introducing it this way. Yeah. This was the state of the art way to look at this for years.
And I can imagine, I mean, I wasn't around during that time, but I can imagine that this is a complex enough thing to think about that only people who really cared to really look into it and learn it and were super interested in it would use a technique like this, because it requires some sort of contextual idea about, okay, you basically have to have already understood the concept of the ALS XZ ring. And then you said, well, let's look at this ALS XZ ring in a slightly different way. And there's limited scope to how you might apply that. That's at least how I'm thinking about it.
Yeah, I mean, that was kind of the process that I went through with this. Tattooing Sunset was the very first puzzle that I published on a forum, and the very first solution used an MSLS, and I had no idea what it was. Yeah. And months later, probably, I was trying to figure out how this worked. And I remember asking the same user about it, and they kind of talked through their process for spotting them. And it's actually very similar to how we find the partitions for set. But without that background of almost like sets, and without the framework of set that we have now, it's really hard to see. I could look at one in a solver and kind of understand what the logic was, but actually finding the thing was impossible. It really wasn't until Trevor Tao did his wonky fish thing that I really started to understand how it would work. So if you're struggling to understand the MSLS side of this, there's a reason that we're talking about set instead now.
Yes, this is actually not a discussion about MSLS. Right. This is a discussion of, this was the state of the art before set. Now let's look at set and see how
Right.
it encompasses MSLS and more, potentially. And it's easier to understand, hopefully.
Right. And one thing I want to get across talking about MSLS is that you can kind of see where it's an extension of fish in some way. Instead of having base sets, our base sets are kind of the cells. And in the terminology that's usually used for MSLS, they talk about truths. So these 8 cells have to contain 8 digits. Those are truths. There are 8 truths. And then just like fish have cover sets, what we're talking about here with 1, 2, and 3 can only appear 3 times in a row together. That's a cover set. We're kind of covering these 8 cells with these 2 rows and these 2 columns, but on specific digits. And arriving at equality.
And the cover rows and columns end up covering every possible candidate.
They end up covering every candidate. Yeah. With regular fish, you're only looking at 1 digit at a time. So you're covering every cell. But really, you're also covering every candidate because there's only 1 digit that you care about.
And I think
I
think it helps me understand, like, why did we choose rows for 1, 2, 3 and columns for 6 and 9 without basically going backwards from, well, I know this is a ALS XY ring and the 6 and 9 are special, right? Because it almost feels like begging the question of, well, I already know that this is here, so here's how I'll describe it. But I think that the way you described it there really helps because it's like, okay, well, I can cover 1, 2, 3 and 2, 3, 4 using the rows. And then if I sort of imagine the 1, 2, 3 and 2, 3, 4 as fulfilled, the only thing left is 2 6s and 2 9s that I have to cover, and they happen to be coverable by 2 columns.
Yeah.
So now the question I guess that I would have is, now that we've fulfilled those truths, is there a limitation to how many cover sets I can actually use for this MSLS?
No, not really. And the example we're about to look at basically has 8 cover sets, if you want to think of them as cover sets.
Okay.
So let's look at it.
Yeah.
That's not it. All right. So this is set theory. So I'm going to look at it with 2 different approaches. Simon, when he did a follow-up video on Tattooing Sunset and kind of explained MSLS.
Yeah.
And the version that he explained is totally valid. It's just not usually how you see it presented when somebody's actually solving a puzzle using MSLS, using the full terminology. But it's a good starting point for talking about it. So in this puzzle, let's see if I can remember where I want to start. I'm going to look at columns 3, 4, 8, and 9.
Okay.
And the reason I'm going to look at those columns is those columns contain a lot of the digits 3, 4, 5, and 6, and not a lot of the other digits. There is a 7 in column 3, but otherwise there's no 1s, 2s, 9s, 8s, 7s. Just that one.
Okay.
I'm going to highlight those in blue. So, of the digits 1, 2, 7, 8, and 9, how many do we need to have in those columns?
4 of each, with 3 7s.
4 of each, but 3 7s. We'll go ahead and say 4 7s and just count this one.
Gotcha.
Yeah. So 4 of each, so 20 total. And we have 1. Yay. So we need 19 more. Okay. Mm-hmm. So most of the rows could contain up to 4 of those, right? In those columns.
Yeah, right.
So, well, there are some givens in some of them. So this row, it can only contain 2 of those digits because there are already givens there. There's actually not a completely empty one.
And just to say again, we're looking at all the digits that aren't 3, 4, 5.
Yeah. Yeah, we're looking at
6.
These digits.
Yeah.
I will just go ahead and highlight them in orange. just for contrast. So
1, 2, 7, 8, 9. Is that what we're looking at?
1, 2, 7, 8, 9. So just looking at the row that we already have a 7 in, those 4 cells could all be from 1, 2, 7, 8, 9.
Well, there's a 2 in the row, isn't there?
Can't be 2, but these could still be 1, 8, 9, right?
Okay. I see.
Those could be 8, 1, 9. Okay. Otherwise, they're limited in all of the rows, right? In some cases, they're limited by givens that are already there. And in some cases, they're limited by them being in those rows.
Gotcha.
So this is the key part of MSLS. Already, we can say we can't put any 1, 2, 7, 8, 9 in those cells because there's other givens.
They're occupied by something else. Yeah.
Right. The key observation, though, is we can only put 2 of them in those cells because there's already a 7, 8, and 9. We could put a 1 and a 2 somewhere in those 4 cells. We don't know where, but we could put them somewhere. But that's it. We can only get 2 that way.
Okay. So we're going to start counting, basically.
We're going to start counting.
We want to get to
we can put
20.
2 in the first row. We can put 2 in the second row.
That's 4.
We can put 3 in this row.
7.
We can put 1 in this row.
8.
And we said we could put 4, counting the 7 that's already there.
Right, we're at 12 now.
We can only put 2 here. We could put a 7 and a 9.
It's 14.
We could put a 7 and an 8.
16.
We could put a 2 and an 8.
18.
And we could put 2 of them down here.
So that's 20.
That's 20. And that's how many we need in those columns.
Which
so
means, sorry, if I can make the conclusion then, is, because I feel proud of myself for understanding it, because this actually feels similar to how we solve a lot of specific Sudoku variants. Like, if we were talking about minimizing sums or maximizing sums on like a little killer or on arrows or things like that, if you solve those, you often sum everything up and go, oh, that's the min and the max, therefore that must be what it is. So this feels a lot like that, except we just did within Classic, where we said we can only fit 20, we counted to 20 of the candidates, and we need 20 of them. So therefore, the cells that can contain them must contain them.
Right. Yep. And so the result of that is we must have a 1 and a 2 in these cells. We must have a 7 and 9 in these cells. We must have a 7 and 8 in these cells. We must have a 2 and an 8 in these cells. We also must have 2 of those digits in these 2 cells, and so on.
Which means we could eliminate...
We can eliminate...
like a 3 from the 2 that you highlighted,
right? Yeah. So we can eliminate 3, 4, 5, and 6 from all of these other cells.
Yeah.
Right? All of these. None of those can be 3, 4, 5, and 6. And additionally, none of the other ones in the limited rows, so these cells, none of those can be 1, 2, 7, 8, 9.
Right.
Some of those were already restricted. So as you can see, there are a lot of eliminations from MSLS. It's a very powerful technique. Some puzzles are going to have them, and they're not actually going to help you solve the puzzle. But when they do, they usually make it collapse significantly.
Yeah, whenever you're eliminating that many candidates, it's
a lot of candidates.
It's useful in some way.
Yeah. So this just occurred to me talking about this right now. This is kind of a halfway approach between MSLS and Set. What we were just looking at. We were doing a counting argument, and Set is a lot about counting. This is kind of how I see MSLS presented when it's being used to solve on the forum that I frequent, where I learned about MSLS. And it's using the same approach that we already looked at of truths and links. So truths are conditions that we have to meet, and links are how we can meet them. And the goal is to have the same number so that we just barely can meet all of our truths. So all of our links must be doing that.
Okay.
So rather than looking at just 1, 2, 7, 8, 9, we're still going to look at 1, 2, 7, 8, 9 in the rows. So we can only have a 1 and a 2 in these 4 cells. We can only have a 7, 9 in these cells, and so on. Right?
Yep.
So 8 digits. But we have 16 cells. So the other links are in the columns on the other set of digits. So in this column, we already have a 3 and a 4. So the most from 3, 4, 5, 6 that we can have is 2 digits. In this column, we already have a 5 and a 6. So at most, we can have a 3 and a 4. Same in this column. And in this column, we can have a 4 and a 6.
Right.
So we can fulfill the candidates in these 16 cells by taking 8 digits from our rows, from 1, 2, 7, 8, 9, and 8 digits from our columns from 3, 4, 5, 6.
So these are the 8 cover sets that you were talking about
Yes.
before.
Yeah, 8 rows and 8 columns. And the way you would notate that is you would look at each candidate individually, together with the row and the column or the box that's covering it. So you would say my link is 1 and 2 in row 1, and my link is 7 and 9 in row 6, and my link is 3 and 4 in column 4. Because again, it's not, the cover sets are really covering candidates. They're not covering cells. So you're specifying that. But the important thing is 1 and 2 and 7 and 9 in this row and so on. And then 5, 6 in this column, 3, 4 in this column. If I marked off all the candidates in the cells, those would be precisely the candidates that can be in those cells. It would basically cover all of our candidates.
Gotcha.
Just like how in a fish, our cover sets cover all of the cells where that digit can appear. This would account for all of the candidates in those 16 cells.
Yeah, and like you said, this does feel a lot more like how we talked about fish rather than how we're going to be talking about set, or like the counting even that we did.
Right. Set is basically the inverse of MSLS.
Okay.
So it's backward fish logic. But there's a lot of overlap, and there's a lot of equivalence, and that's why I stuck that equivalence in there with the double meaning.
Yeah.
Yeah. So that's how MSLS works. You have 16 cells. They need to be filled with digits. You can get 8 of those digits from 1, 2, 7, 8, 9 in the rows. You can get 8 of them from 3, 4, 5, 6 in the columns. So those rows and columns in your MSLS, in your green cells here, must contain those digits. So 1 and 2 must appear in these 4 cells somewhere. Gotcha. So just like before, we can eliminate 1 and 2 from the other cells in the row. The row is the cover set. We're eliminating the cover cells, or the cover candidates, I should say, that are not part of our MSLS. So 1 and 2 can't appear there, 7 and 9 can't appear there, and so on. So that's the MSLS approach.
Gotcha.
All right. Hopefully it makes a little more sense, and you can kind of see how you might solve a puzzle like that. Ultimately, the things that you're looking for are groups of digits that occur together. I'm just going to go ahead and highlight these. So in the blue cells, we have a lot of 3, 4, 5, 6. In the red cells, we have a lot of 1, 2, 7, 8, 9. And they don't see each other very much. Apart from the 7 right here, they don't see each other very much. The green was our MSLS. The red and the blue are our set partitions. So it's really just the complementary way of looking at it. All right, so let's look at something that everybody should be familiar with if you're watching this, but in case you're not, this is the Fisto-methyl ring, as it's referred to.
Which is named after the constructor who popularized it in one of his puzzles that was featured on Cracking Cryptic. So.
Right, and from what I recall, Fisto-methyl didn't want to release the puzzle until a way was found to solve it without the Fisto-methyl ring. I think it was a killer, probably. I don't remember what variant it was.
I wish I did remember as well, but that's not important.
Not important here.
Nowadays, people release puzzles that absolutely
all the
intend
time
to use it. So,
or worse.
Yes, or worse.
Yeah. So, this is the Fisto-methyl ring. We talked about this a little bit last time, but these 16 cells in blue have to contain the same digits as the 16 cells in orange. There are a few different ways you can arrive at that conclusion. The original way I saw this proved is probably the most confusing way that I've seen to look at it.
That makes sense because people have refined the explanation over time.
Right. So we looked at it last week briefly, talking about mutant fish, I believe. Right. So that's kind of the box approach. So let me just get rid of all of our highlighting for a second. If we add boxes 1, 3, 7, and 9 to blue, let's say, I'm going to end up inverting my colors, but that's okay. And then we put rows 3, 7, and columns 3 and 7 into orange. I think I have multicoloring off. Oh well. The overlap is part of both. We're just going to ignore that. And that's what we're left with. So we added 4 sets of 1 to 9, and we subtracted 4 sets of 1 to 9.
And the reason the corners stayed orange is because they overlapped in the rows and columns. So they ended up getting added once or subtracted once, which removed them. But then the overlap then subtracted them again, which adds them to the other set. So
yeah. So this 5 is part of box 3 that we put in blue, but it's also part of row 3 and column 7. So we put it in orange twice. So the net result is it's in orange. Yeah. The way I wrapped my head around this is different.
And feel free to turn on multicolor if that's helpful.
Oh yeah, I should do that. That will help a lot. That's not going to help with this particular way of looking at it, but that's okay. Because I didn't really look at it with intersections per se. I looked at it with different sets being equivalent through math, basically. It amounts to the same thing. So just looking at the orange cells all together, including the central box, if I add the green cells, I get all of columns 3 through 7. So 5 total columns. That gives me 5 sets of 1 to 9. And I'm going to subtract the central box. So now I have 4 sets of 1 to 9. If I look at blue and green together, I have 4 complete rows. So again, I have 4 sets of 1 to 9. So blue plus green is equal to orange plus green after I get rid of the central box. And since the green is the same in both cases, I can just get rid of it too. And we're back to our Fisto-methyl ring in the corner boxes. So several different ways you can look at it. So obviously this excited a lot of people. It is still common on Discord for people to come in talking about variants of Fisto-methyl. And that's great. if it's the first time you've seen Fisto-methyl and you are independently looking at ways to mix it up, that's great.
I think that's evidence that it's an approachable theory to use.
It's an approachable theory, and it's a really cool theory.
Yeah.
Yeah.
It's exciting, it's approachable, and it's understandable enough that a lot of people independently go, oh, you can draw more than just the Fisto-methyl ring using these strategies. Let's experiment.
So let's switch to our sandbox here and just play around.
You can turn on multicolor again.
Yeah, definitely turn on multicolor. What do you want to
add? Well, let's do the expanded Fisto-methyl ring, because I think a lot of people kind of first go to that one.
You want to know the 2-8?
Yeah, the 2-8.
Okay. So we'll start again by adding the corner boxes.
Yep. And why don't you do rows first, resolve that, then do columns. So I think that's easier to understand.
Sure. So we're going to put rows 2 and 8 in orange. David's been saying subtracting, and I'm going to talk about the adding and subtracting in a little bit as well. But the result is if you put these in blue and in orange, they kind of cancel out.
And the way to think about that is, if you put them back for a second, sorry, I just want to, for the visual aid. So whatever cells are in blue, we're trying to make those equivalent to whatever cells in orange. So right now what we can say is the blue cells are 4 sets of 1 to 9, because we used 4 boxes, and we know each box is 1 to 9. Then the orange cells are 2 sets of 1 to 9, because we added rows 2 and 8 to the orange. So I know I'm saying the word add, but in this case I'm just saying we have made 2 rows orange, therefore orange is 2 sets of 1 to 9. We made 4 boxes blue, that's 4 sets of 1 to 9. And what we can do is, if we want to make an equivalence for blue and orange, what we can say is blue is orange plus 2 sets of 1 to 9. Now, we know of 12 cells that are definitely in both blue and orange. And those cells, whatever it gets filled in them, will be covering, if we want to use the term cover, they'll be covering those numbers in both of those colors. And so if we just remove those 12 cells, which you can just hit redo to do that, just remove those 12 cells, now we haven't broken that equivalence. We've preserved the equivalence that orange or blue is orange plus 2 sets of 1 to 9. We haven't broken that because whatever we've removed from one set, we've also removed from the other set.
Yeah. Ultimately, what we're trying to do is end up with a set of cells that's in blue and a set of cells that's in orange, and show that they're equivalent, or equivalent plus or minus sets of 1 to 9.
Yeah, so we could stop here if it was useful, but we don't have to stop here. Right?
Sure. So any cells that end up in blue and orange, those are already taken care of. Additionally, I'll just mention this while we're doing, if we have a 2 here and a 2 here, we can take those out.
Yep.
And this is something that I actually don't ever do. I always leave all of my highlighting, but David, when he solves using set, always removes digits that are already taken care of, which is smart. It's just not something I do.
Yeah, I mean, everyone's got their own styles, right? But I find it easier because now I don't have to worry about those digits. Sets anymore.
Yeah. All right. So to complete this, now we're going to look at columns 2 and 8.
And do the exact same thing we just did.
We'll put them in orange, and then we're going to get rid of the cells that are now in both. And that's what we're left with.
And so this kind of looks like the Fisto-methyl ring if you kind of blew up the Fisto-methyl ring, right?
Right.
So we still have 16 cells in blue and 16 cells in orange, but they're kind of overlapping in a slightly different way. And so you can easily construct some kind of puzzle using this set instead of the Fisto-methyl ring, right? Yep. But it's still, the process is exactly the same. We used the same 4 boxes, we just used different rows and columns to construct it.
Yep. My other personal favorite variant is this one. And I'm not going to go through all of the explanation for it, but it is equivalent to
So we'll leave that as an exercise to the viewer to prove to themselves that those sets are equivalent. I think we could go over the really common ones that people are going to encounter, because people tend to copy each other's sets rather than inventing their own.
Yep.
And there's two reasons for that. One is because those are the ones they know, but also it's because those are the ones other people know, and they want at least their break-in to be approachable without having to rediscover whatever set they randomly used.
Yeah.
So I think that the two we could show are the Advent Vettering set. Are you familiar with that one?
Yeah. I may get it slightly wrong. So
we do four rows at the top and then 5 columns on the right side.
Oh, that's right. Yeah. So put all these in blue. I'm going to put all of these in orange.
And you just kill the remaining. And so now you can get rid of box 9. And
so those are equivalent.
Those are equivalent sets. So, because we started with 4 rows on top. So blue was 4 sets of 1 to 9. And then we did 5 columns. So it's 5 sets of 1 to 9. And then we removed a box from orange. We can also remove a box from blue.
Yep.
And it's now imbalanced, but sometimes this is also quite useful. I think this might have been offset. I don't remember exactly how this specific puzzle was done, but there's a lot of variations of this one. Yeah,
so usually with set, any time you can just get rid of a box, it's probably a good thing to do.
It's probably a good idea, yeah.
If you end up with a complete box or a complete row or a complete column or some other complete house as part of one color, part of the added set or the subtracted set, then it's good to remove it because you're dealing with fewer cells.
And so often what will happen with break-ins that use this set is the equivalence here is orange is blue plus a set of 1 to 9. Now, if you can use some kind of constraint or cleverness to show where one of 1 through 9 are in orange, then those can be removed, and now the blue and orange are equivalent.
Yep. You can also use it other ways. So, just as a quick example, this may not be a solvable puzzle, but that's okay. Let's say we have and hopefully I don't get too many digits. 7. One more. Yeah, one more. Really, I don't need the 5. Great example. All right. So I have 2 1s, 2 3s, 2 7s, and 2 9s in orange. Because orange has an extra set of 1 to 9, I can kind of get rid of one of each, but I still need one of each in blue, and there's only 4 cells. So this would be forced. These 4 blue cells have to be from 1, 3, 7, and 9.
Yeah, because the plus 1 to 9 that we're adding to orange to make them equivalent can only take care of one of 1, 3, 7, and 9.
Yeah.
And so there's still another 1, 3, 7, and 9 that the blue has to accommodate.
Yep.
Or the puzzle's broken.
And this is a pretty common thing to see using set, where you have an imbalanced set. So the other one, I actually had this one prepped, but we'll just go through how you can generate it. So this is what I think of as the odd-even partition. So row 1, 3, 5, 7, 9. Let's add 2 orange. And then we'll do columns 2, 4, 6, 8. So we're doing the odd rows and the even columns. And we're going to put those in blue. And then get rid of... Can I double click? No.
Yes, you do.
Get rid of all of the multicolored cells. So in this case, orange is blue plus one extra set of 1 to 9. Since we added 5 rows to orange and we only did 4 rows to blue. Yeah. This, again, is when I was originally doing things like this, I didn't think of them in terms of adding and subtracting sets. I thought of them as intersection problems. So actually, let's do that. So the way I would have looked at it is orange plus green is 5 rows and blue plus green is 4 columns. It amounts to the same thing. The green cells that we're adding to both and then eliminating, those are the cells that we're getting rid of the highlighting on. So it's the same thing. Yep. But this is actually how set started to be generalized. So Fisto-methyl did the Fisto-methyl ring. Let's do purple for that. Fred Stadler on the forums talked about some generalizations. They were already talking about variants of Fisto-methyl, just picking different rows and columns. But Fred pointed out that you could pick any arbitrary number of rows and any arbitrary number of columns. It didn't have to be 4 and 4. You didn't have to end up with an even count. And you didn't have to have a situation where you can get rid of box 5, say.
Yeah.
Entirely. So you end up with this kind of plaid pattern, which I've seen in a number of different color schemes. But
yes.
This was kind of the next step.
I kind of want to get a t-shirt. Maybe slightly different colors, but
right.
My set
this
t-shirt.
This is not an appealing color scheme to me. So yeah, Fred did that. I mentioned the wonky fish. I'm not going to go over the wonky fish. I definitely suggest, though, that you search for wonky fish on YouTube. It should come up. It's a video by Trevor Tao solving Tatooine Sunset. And the way that he looked at it was more dividing the grid up into separate 3x3s and showing that there had to be so many of these digits in this set and where are they going to appear elsewhere in the grid. So it was kind of a expanded version of set. Not just 2 partitions, but 3 almost. It's a very interesting video, and especially since we hadn't developed all this terminology for it at the time. Really impressive. But that kind of kicked off a discussion. Tom Collier on his blog was discussing these things. And Sam Kappelman-Lynes, who has been doing Sudoku for quite a while and is very familiar with advanced techniques, knew about multi-sector lock sets. And he is kind of the one that came up with the idea of adding and subtracting. So giving rows a +1 and columns of -1, and anywhere you have a +1 and a -1, well, that equals 0. So you can ignore it. So that's how we ended up doing it the way we do it. And then we gave it a fancy name, and here we are.
You gave it a fancy name, it's my understanding.
I did give it the fancy name. Yes. I'm not going to talk about the other fancy name that I gave, which is Phil. Maybe next time I will go over Phil.
Okay.
All right, so let's see this in a practical application. So let's get rid of all of our highlighting. This is set theory again. The way I usually approach looking for set, like same as we talked about for MSLS, you want to look for digits that keep lining up. So I see 987 here. I see 821, 912. These are a lot of overlapping digits. I might even look at this 2 and the 7 and start to put them in that partition. So what I might try is adding all of these rows or columns, whichever makes more sense.
Column kind of seems to grab digits we don't want, though, so rows makes more sense in this case.
Yeah. It's going to usually be equivalent, but let's try adding this row. We'll see why we don't really want that row once we do it.
Okay.
So now we're going to look at the other digits that don't appear in these rows. And they mostly appear in a few columns, right? There's one over here. That's only one digit, and there's 3 from the orange set in that column. So we're not going to add that column to blue, but we'll do the other ones. So we're going to put these in blue.
Oops,
and I forgot to turn on multicolor. Let's turn it on. And we'll just get rid of these. All of these. So that's a partition that I could have.
And it's imbalanced.
It is it is imbalanced. Now, I believe this is usable. Let's check it and see if it's usable. So it's imbalanced. Do you want to look at the blue digits or the orange digits? It's the same either way, but
let's look at the blue digits.
Okay. So we have 2 3s, a 4, 3 5s, and a 6.
2 6s.
2 6s. That's 8 total digits. So how many of those digits do we need in orange?
Well, we need the ones that are in blue plus a full set of 1 to 9, so 1 extra.
Right. So in total we need 12. 8 plus 4. So the 4 is because we have 4 digits that we're looking at. So empty cells, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
Wow. Doesn't always work out this way, but...
So since we need 12 of those digits in those 12 cells, they have to be from 3, 4, 5, 6.
And the important thing to point out is none of the orange cells were already 3, 4, 5, 6.
Right.
Had they been, using my technique of canceling them out can help visualize that.
Yes. So just because we did this for the MSLS example and because it gives a balanced set, let's say we hadn't put that row in orange.
Right.
Just to see what that would look like. So this is an example where we can cancel out. There's a 7 in orange and in blue. So
you can just pick any of the 7 in orange if there's more than one.
Yeah. It doesn't matter which. So this time it's balanced. We have the same number of cells in blue and in orange. In this case, we would have added 4 rows and we would have added 4 columns.
Mm-hmm.
So we still have 8 of the 3, 4, 5, 6 digits in here, and we only have 8 orange cells. But we don't need that extra set now.
Great.
So logically, these are completely equivalent. There's no reason why you couldn't use this version or the previous version. What the previous version did was tell us that these cells are 3, 4, 5, 6. What this version does is tell us that these cells are 189, which amounts to the same thing. If these 3 blue cells are 189, then these 4 cells have to be 3, 4, 5, 6.
It's just the 2 tuples that
right
end up happening.
Yeah, we just inverted which one we're going to use. So yeah, that's the type of deduction that it gives you.
And
MSLS,
just to mention it,
yeah,
you don't just put blue into orange. You can also look at orange and put it into
yes.
blue. You get both equivalencies.
Yeah, so what I was going to say is MSLS looked at eliminations, right?
Yeah.
So the key difference with set, and part of why I think it makes it a lot more intuitive to actually deal with, it's easier for me to find because it's kind of the same way that you would be looking for multi-sector lock sets anyway. You're looking at digits that are aligned like this. Mm-hmm. But what feels really natural to me is because I need 8 digits from 3, 4, 5, 6, I can just put those 3, 4, 5, 6 candidates in those cells. And because I need 11 more digits from 1, 2, 7, 8, 9, I can just put those in those cells. I'm not having to keep track of, well, okay, so 1 and 2 had to be in these 4 cells, so I'm going to eliminate 1 and 2 from these cells. I'm just immediately writing in what the candidates are. And then you can reduce these based on givens that they see. So that can't be 8, 9, for example.
You can do this from the very start of the puzzle without having filled any candidates ahead of time, which is also, it just speeds up the solve, to be honest.
And that's an important thing to mention, actually, is puzzles that are designed around set, often you want to do them from the very start of the puzzle because it's a lot easier to see.
To be fair, though, sometimes the constructor's clever and hides some hidden singles or naked singles somewhere that are important. But.
Yeah, sometimes you need to get a hidden single. Let's look at one more example where that's the case. Get rid of that 5 there. So you want to have a stab at what the set is here?
Okay, so I've got 6, 7, 8, 9, and 1, 2, 3, 4. I'm not sure where 5's supposed to go. Probably with the 6, 7, 8, 9s. So I know our fishes were on 1, 2, 3, 4. So I would maybe make that one set, and then 5, 6, 7, 8, 9 another. So I'm seeing row 2, row 4. That row 6, and then row 8. Those encompass just those 5, 6, 7, 8, 9s, and then I could do
turn multicolor on.
Columns 3, 5, and 7 are going to give you, and the 5s are maybe going to cancel a bit. But.
Okay.
And I need another. Well, it's a bit imbalanced. I don't know if we can keep it imbalanced or if we want to add another set somewhere. But
we can try it like this.
Okay.
If you want. So like you were saying, we can actually eliminate all of the 5s here.
Right. Okay.
It is imbalanced, so we have an extra set of 1 to 9 in blue. So let's look at the digits in orange. So we have 6 digits, 1, 2, 3, 4. How many digits do we need in blue?
So an extra 4 on top of... Yeah, because there's 4 candidates, so we need an extra 4 on top of the 6 that you have highlighted. So we need 10 total?
We need 10 total from 1, 2, 3, 4.
Yeah.
But we also need a 5.
We also need a 5, true. So... I mean, that's the hidden 5.
It's a little tricky,
right? But
yes.
If we didn't find the hidden 5, I'm wondering if this set still works or if we have to...
I think it does. But that's something you have to be careful of when you end up with none of a digit in either set.
Right.
If it's imbalanced, you still have to account for it.
We should recognize that both orange and blue do not have a 5, but we know that blue has an extra 1 to 9 in it, so blue does need a 5 in it.
Or equivalently, they both had 2 5s to begin with. But because orange is the smaller set, we're going to include 5 in orange because we're going to need 1 extra 5 to go in blue. Yeah. So if we look at blue, we said we needed 11 digits total, right? And we have 11 empty cells.
Yep.
So that worked out. So we can immediately say 1, 2, 3, 4, 5 for those cells. And we can immediately say 6, 7, 8, 9 for those cells. Now let's look at it the other direction just to see how it works if you're looking at it from the larger set first. Okay. So we have 9, 8, 7, 6 in 11 cells. That worked out nicely.
Yep.
Nice and balanced. So if we're going from blue to orange, blue has an extra set of 1 to 9, and we're looking at 4 digits. So we subtract 4 from our 11 to get 7, and we have 7 orange empty cells.
There you go.
So that works. Now, where does 5 actually go in our blue? This may not
going to show us our hidden.
I don't think it is quite.
Yeah, it's not.
So it can't go in any of those, but it could go up here or it could go here. So that's where you have to keep looking sometimes to find your singles. In this case,
you have to find hidden singles. You can't just use set for the entire set.
Right.
Okay.
In this case, though, if this was the set that we used, and then we realized there's a 5 there, we only needed 1 5 in blue.
Yeah.
So we can immediately eliminate these 5s.
It's helpful to remember how many of each digit you wanted in each set. So once you find all the ones you needed, you can immediately eliminate them from the other ones in the set.
Right. So the set I had in mind with this was actually the odd even.
I figured as much.
Which there are usually multiple ways to do these, so that's fine. But it works kind of the same way in reverse. This time orange is the bigger set.
Right.
So we need extras of 6, 7, 8, 9, and we need fewer of 1, 2, 3, 4. I'm just gonna get rid of pencil marks. That didn't work. Keep our 5 there. So in this case, we have a 1, a 2, 2 3s, and 2 4s. But orange is the bigger set this time. So we're going to take those 6 digits and subtract 4 to get 2, and we only have 2 cells. We need an extra 3 and an extra 4. So they have to go in those cells. And this one sees a 4. So that's the 3 and that's the 4.
That just gives you the...
Yeah. And then if you continue from there, none of the orange cells now can have 1, 2, 3, 4, or 5. None of those cells can. They can 5. Sorry, 5's fine, but they can't have 1, 2, 3, 4. So if they can't have 1, 2, 3, 4, where do 1, 2, 3, 4 go in those rows and columns?
Yep.
So 4 hidden quads.
And that's what we would have found with the 4 fish that we were talking about on this one before.
Yep. So that's how that works. That is basic set. Set for classics, most of the time you can get away with just rows and columns for your set. Sometimes you need boxes, and boxes are perfectly fine to use. I see boxes more often in variants. So just to talk about that a little bit, if you're doing a variant and you're wanting to use set, you can use any set of 1 to 9 to add and subtract. So 9-cell killer cages, they're a set of 1 to 9. Extra regions, anything you want to use. Diagonals.
Nice.
They're a lot harder to see once you start introducing variants. So you have to, if you're setting puzzles, you have to be very careful how you use this, because you can come up with something crazy involving disjoint groups and killer cages and end up
irregular regions. And
yeah, I'm thinking of Glum Hippo's puzzle that nobody's been able to figure out a solution for yet.
Well, we know the solution. We just don't have a logical path.
We don't have a logical path for it. There are just a ton of ways that you can try and use set in that puzzle. And if there is a way to use set in that puzzle, it's a very confusing way to find. Yeah. So it's something you have to be careful of as a setter, to make sure that if you're using set, you're doing it fairly in a way that somebody's going to be able to figure out.
Also, I have absolutely no problem with people who use some sort of pun in the title to imply that set is going to be used in the puzzle, just to sort of go, spark that, oh, maybe I should be looking at sets here instead of trying to do normal Sudoku and then trying to do fishes and all this other stuff. If your intention is the break-in is set,
right,
and you put something that alludes to that in the title or description of the puzzle, then that can save your solver a lot of time.
Yeah, the first couple of set puzzles that I posted on Discord, I definitely included some sort of pun.
Yeah.
It's become a lot more common now to look for. One more thing I wanted to mention on basic set is what we've talked about with classic Sudoku is equivalence between two partitions, forcing one set of digits to go in blue and one set of digits to go in orange.
Right.
With variants, especially killer cages, little killer arrows, anything with sums, a lot of times you don't really care so much about what the specific digits are. What you care about is the minimum and the maximum. So that's where I've seen Fisto-methyl in particular shine. It's usable in classic, but it's a little hard to set a puzzle specific for the ring. But when you add in killer cages, then you can do some neat tricks with sums. Okay, so that's the main basic stuff. This is going to be at least a 2-part. There's a lot more of set stuff to talk about. So one thing I will mention, I have 2 puzzles for you guys to try. One of them uses basic set. It's actually going to be our first puzzle by a guest setter. This is one of Jovial's puzzles. So that one uses basic set. The other one I'm going to share does not use basic set and is very hard. So you may struggle with it, and that's okay.
Is it as hard as Chironix? Because I'm a little worried. But
so it's somewhat infamous. Mm-hmm. So it's Garam Masalas.
Okay.
I don't know if that's actually how you pronounce that, but that's how I pronounce it.
Okay.
And this came about where I was messing with almost MSLS and almost MSLS. And so I just started sticking A's, and so that's where the Masalas comes from.
Gotcha.
But, so you have to do something tricky in that one. Just to give you a warning. We will talk about that one in more detail next time. And some of the other tricks that you can use in set. Generalize it as much as possible. But.
Great. And my expectation is if I were to put that second puzzle into a computer solver, it would tell me to do all sorts of crazy chains and dynamic verities and contradictions. And
yeah, it's not as bad as set theory in terms of putting it into a solver that doesn't support it. Mm-hmm. But yeah, it needs dynamic chains, if I recall.
Great.
Yeah.
All right. Well, thank you, Philip, for this awesome explanation of set. Like we said, this is episode 1 of at least 2, where we will be covering set. It's a huge topic, and there's a lot more to be done. I'm very interested in getting to some of the more advanced stuff with set that Philip's been researching. He's released some very interesting PDFs that I don't quite understand. So I'm hoping he'll explain it to me while he explains it to you as well. So
yeah, as far as classics go, this is probably the thing that I spend the most time thinking about. So I have a lot to say about it.
Yeah, there you go.
Yeah.
All right. Well, thanks everyone for watching. And please, if you are not subscribed, please remember to subscribe and hit the notification bell if you want to see when I go live streaming or upload a new video, whether it be another Sudokult discussion video, which we are trying to do every 2 weeks. We had a little hiccup last week, and so this one's a week late. But from now, it'll be hopefully 2 weeks from now for the next episode. Yep. And also, if you check the description, I do have a new Patreon. If you'd like to support the channel on a consistent basis, feel free to sign up for the Patreon as well. It is minimum $1, but you can, of course, pledge as much or as you'd want above that. And other than that, thank you, Philip, again. And thanks, everyone, for watching.
Bye, guys.
Bye.